On February 6, 2023, two earthquakes rocked the border between Turkey and Syria.
Turkey-Syria earthquakes were really large earthquakes, not to mention incredibly damaging.
Over 56,000 people died, with the damage to both countries incalculable. Could scientists have seen the 7.8 magnitude disaster coming?
Earthquakes maintain the dubious distinction of being the only large-scale natural disaster for which we have no real prediction.
The places that have had large earthquakes in the past are the places where we know there will be large earthquakes in the future.
But will the world's seismic experts ever be able to predict the next monster quake? Being able to forecast killer quakes could save thousands, even millions of lives.
Earthquakes are scary, they happen without warning, and people want something to tell them, this is coming, this is what's happening.
Experts are racing to find a way to know where and when the next big one will strike.
So is there a threshold for how big this zone is before a fault starts?
Yes. If we can understand the past, then we can prepare for what's eventually going to come our way.
Turkey's 7.8 earthquake was a big one, but not the largest we've seen in human history.
What happened in Turkey, though, is we had two earthquakes. We had the initial large earthquake that was about magnitude 7.8, followed very shortly afterwards by a magnitude 7.5.
The surface of the Earth is covered with a thin skin of rock called the crust. And the crust is broken into these big pieces that are moving around very slowly. And the places where those tectonic plates, those pieces come together and touch each other, are the places where we have the most earthquakes. Those plates are moving. They're causing stress and strain to build up in the rocks where they're touching. Sooner or later, that's going to overcome the strength of the rocks, causing the rocks to break. And when the rocks break, it sends energy out in all directions, and that's what we call an earthquake.
Earthquakes are rated from 1 to 10 using the Richter scale, with 10 being the strongest possible magnitude.
I like to think about the spaghetti magnitude scale. So if we have one strand of spaghetti, let's imagine this is a magnitude 5. So what would a magnitude 6 be? A magnitude 6 would be 32 times larger. So that would be 32 strands of spaghetti. That's going to take more energy. What about a magnitude 7? A magnitude 7 would be 32 times larger. So that's 1,000 strands of spaghetti. So this is significantly more than that last one that we just broke. What about a magnitude 8? That would be 32 times larger than this. So that would be 32,000 strands of spaghetti.
A magnitude 1 releases as much energy as 6 ounces of TNT, while a magnitude 8 earthquake would be the same as detonating 6 million tons of the same explosive. There has never been an earthquake with a magnitude of 10.
We have never recorded a 10.0. We don't have any geologic evidence of one. The largest earthquake we've had was in Chile. It was a magnitude 9.5.
On May 22, 1960, the 9.5 earthquake struck Valdivia, Chile, in the middle of the afternoon. The monster quake lasted for 10 minutes and triggered a massive tsunami with 82-foot waves, which devastated the Chilean coast, and then raced across the Pacific Ocean to smash into Hawaii.
Tsunami waves travel at about the same rate as a jetliner. And so we know, for instance, when the earthquake happens, how long it would take to get to a certain place on the other side of the world.
Waves as high as 35 feet were also recorded in the Philippines, 6,200 miles from the epicenter. The exact death toll from the Valdivia quake is unknown. The level of destruction caused by an earthquake doesn't just depend on its magnitude. It matters where and when it hits.
Earthquakes don't necessarily need to be large to be damaging. It depends on where they are and how close they are to population centers and how prepared and resilient the area nearby is that experiences the effects of the earthquake.
You can have a smaller earthquake that happens right under a city. It can have very sort of devastating localized impact. So the location very much matters. The local building codes also really are very important. If there are two different, countries, one has strict building codes, the other does not, then the same size earthquake will have very unequal damage in those two different countries, even though if everything else is the same.
The 1964 Great Alaska Quake struck on Good Friday, March 27th at 5:36 p.m. in Prince William Sound. The 9.2 was and is the strongest one in U.S. history, but only 139 people died.
Alaska is such an interesting state because it has more earthquakes than the other states put together. And on average, they have at least one magnitude 7 earthquake in Alaska every year.
The biggest ones, you'll probably have like 3 or 4 minutes of shaking.
At the University of Texas Jackson School of Geosciences, Dr. Chas Bolton studies earthquakes by creating them.
One of the things that allows us to do it is it allows us to understand how earthquakes sort of get started and then how they sort of propagate and actually stop along a fault.
The team has built a machine that replicates the movement of tectonic plates and the resulting impact on rocks.
The big black thing there, if you can see it, is the load frame. These are just kind of steel blocks that are sort of stacked on top of one another. On the outside of it, there's 4 hydraulic rams right here, and a big ram on the back there. Inside the load frame are sort of the 2 tectonic faults. And in between them is a very, very thin layer of what's in between a fault zone. We're monitoring the stress and the strain and the slip at roughly about 10 locations along the fault there. So we can see exactly where it starts and then how it propagates along the fault and then ultimately how it terminates.
The earthquake machine replicates straightforward rock movements and the same seismic processes that create earthquakes in California and in Turkey.
The San Andreas Fault is pretty similar to the East Anatolian Fault.
The San Andreas Fault is a strike-slip fault. The East Anatolian Fault, where the earthquakes in Turkey and Syria occurred, that's also a strike-slip fault.
Strike-slip faults are usually found inland.
It's a place where one of Earth's tectonic plates slides past another. It's called a transform fault or a strike-slip fault.
The quakes produced by strike-slip faults can be quite large, but not as large as those born in subduction zones.
There are subduction zones all around the world. A subduction zone is a place where 2 of these tectonic plates are coming together, and one of the plates is being pushed down underneath the other. And these subduction zones are the places where we can have the largest magnitude earthquakes.
These are large events that are typically very destructive. If they occur in subduction zones underwater, they also typically displace the seafloor, so they would generate significant tsunamis that pose then a related and secondary hazard. The mega quakes, as we call them, are the magnitude 9 class earthquakes. You can count the number that have occurred in the last century on one hand, yet that small number of events, the 1960 Chile earthquake, 1964 Good Friday Alaska earthquake, the Tohoku earthquake, Sumatra earthquake, if you add up the energy of those events, they account for approximately 3/4 of the entire seismic energy release of the last century.
Alaska, along with the Pacific Northwest, Chile, Japan, and the South Pacific, all experience megathrust earthquakes from subduction zones offshore.
In that type of geometry with one plate going underneath the other, you can produce large damaging tsunamis. Whereas the geometry of, say, the San Andreas Fault is not conducive for a tsunami.
Since it doesn't lie offshore, it can't displace ocean water.
In the Sumatra earthquake, for example, it was over 250,000 people passed away, were killed by the transoceanic tsunami. Tohoku, that was a similar story. The ground shaking was damaging and damaged structures, but it was the tsunami that really caused the most loss of life.
After the devastation caused by any type of earthquake, the Earth begins a geological healing process. Brand new research about this process has created a revolutionary tool in the quest to forecast the big ones. Dr. Demian Safer at the University of Texas in Austin is investigating how the speed at which rock recovers can shed light on how soon the next major quake might happen.
After you're done sliding, it needs to re-strengthen so that you can build up stress again. Otherwise, it would just keep moving along peacefully and it would never stick again.
So is there a threshold for how big this zone is before a fault starts?
Yes.
And so rocks in the earth and fault lines in the earth indeed do heal. And that's been a big focus of our recent research, is to try to understand what controls that, how much and how rapidly do those fault lines heal after they've moved, and then how does that healing rate compare with how quickly the stress is building up? Because it's really a competition between those two things, and whichever one wins, if the healing wins, then it will take a long time before it breaks. And if the healing loses, then it will break again sooner.
A fault that is slow to heal is more harmless than one that heals quickly. The latter is more likely to break and result in a large, damaging earthquake. The University of Texas combined an analysis of rock samples from a well-studied fault off the coast of New Zealand with a computer model. The clay-rich samples were drilled from half a mile under the seafloor in a subduction zone.
Monitoring instruments that we are installing offshore in New Zealand are incredibly sensitive and incredibly valuable because these are in a blind spot. If you put instruments in near the trench, you can be within 1 kilometer or 2 vertically above the fault line, and you can see a lot more than when you're on the coast and the fault line is 30 kilometers below you and you have to see through a lot more earth. And so we're able to detect really tiny motions on the fault.
Demian's team squeezed the New Zealand fault samples in a hydraulic press and discovered that they were very slow to heal and slipped easily.
And we shear it under pressure in the lab. And then if you were to look at these surfaces, you can see kind of these striations that form from that shearing. The pressure and temperature are also really important. So if you're deeper in the earth where it's warmer and there's a larger pressure, it may be that healing can occur more rapidly than places that are very cold and shallow.
When the scientists plugged the rocky data into the supercomputer, the results were astonishing. The data predicted small, slow-motion tremors every 2 years, an exact match to actual observations on the New Zealand fault.
One of the things we do know about New Zealand is that most of the motion between the plates is not occurring in large earthquakes, at least in the historical record that we have over the last few decades. It's occurring in these slow slip events. So it can't be strengthening too quickly, because if it were, then it wouldn't fail that frequently. It is kind of an ideal place because it has these recurring and relatively frequent small earthquakes.
Safer's team proved that it is possible to forecast these slow-motion earthquakes that originate from the New Zealand fault, and now they're looking at other faults around the world. The megathrust fault in the Cascadia subduction zone stretches over 600 miles from northern Vancouver Island to Cape Mendocino, California. The seismologists are intently studying this deep-sea trench where monster earthquakes are born.
I would choose not to live in low-lying coastal areas in subduction zones, whether that's Japan, the Pacific Northwest, or New Zealand. The Cascadia subduction zone is probably the biggest earthquake hazard in the US. When you combine the geology with the distribution of population and the time since the last event and kind of expectation of when we're due for another earthquake, all of the concerns do point to Cascadia.
The scientists suspect that the rocks in the Cascadia Fault are something other than soft clay, but the deep location of the subduction zone makes it nearly impossible to obtain samples.
In Cascadia, the suspicion is that there'd be some mixture of clay and sand, or clay and quartz. And so we think that the quartz may be a really important player in controlling the strength and the amount of healing you might get in that fault zone.
Faults with more quartz knit together more quickly and more likely to spawn a serious earthquake. Chaz Bolton is investigating how the composition of the fault rocks factors into earthquakes that occur.
The stuff that we have in there right now is actually 100% quartz, so it's not clay, it's just 100% quartz. And we started off with that because we know a little bit about how it behaves in sort of smaller scale faults, so that's kind of the idea.
The other thing that's really interesting about Cascadia is that the fault is forming at a higher depth and higher temperature than in a lot of other subduction zones.
Most subduction zones are in the Pacific Ocean.
Oh my God!
Because seafloor spreading, the process by which new ocean crust is created, occurs constantly in the Pacific. Cascadia has produced magnitude 9.0 or greater earthquakes in the past, and will continue to do so in the future. Vancouver, Seattle, Portland, and Northern California would be tremendously impacted by a large quake generated by the Cascadia Fault. They're all coastal cities, so the threat of a tsunami is real.
You only get a tsunami if you get a displacement of the water. So what happens during the megathrust earthquake is the seafloor will spring back, that lifts up all the water above it, which then cascades out in all directions as a tsunami wave.
Geological evidence indicates that the zone has seen huge earthquakes at least 7 times in the last 3,500 years, with a return interval of 400 to 600 years. The last known megathrust earthquake in the Pacific Northwest was in 1700, just over 300 years ago.
They figured out when the earthquake was because of records in Japan. The samurai had kept really detailed records, and they knew that an orphan tsunami had occurred and had hit Japan at a certain time. They were able to trace that back and determine that the earthquake in the Pacific Northwest occurred on January the 26th at 9 p.m., based on those records.
The effects are easily seen in the Oregon ghost forests, where parts of the continental crust moved below sea level and salt water killed coastal trees.
After the earthquake, the land dropped, and then it was flooded, killing all the trees. We can actually then date the trees when they died to actually figure out when the earthquake occurred and get an estimate of how large it may be.
South of the Cascadia subduction zone, geologists are also studying the famous San Andreas Fault.
There's a couple of reasons why the San Andreas is such a famous fault. One is because it's the longest fault in California, and so it's capable of producing the largest magnitude earthquakes. Also, the 1906 San Francisco earthquake occurred on the northern San Andreas Fault, and that earthquake was really what started earthquake science in the United States.
The San Andreas is not a subduction zone, and it creates strike-slip earthquakes.
The San Andreas Fault, particularly in Southern California, you have granite. The question is what else is in there and how much of the fault rock is clay. On the San Andreas, it's some clay, but in some parts of the San Andreas, there's also a lot of quartz. And quartz is a mineral that is typically stronger and has a higher rate of healing.
Because the San Andreas Fault heals more quickly, it's ripe for larger, more damaging earthquakes. The two tectonic plates are slowly moving past one another at a rate of a couple of inches a year, about the same speed as fingernails grow. Scientists at the University of Texas are getting very close to understanding when and how violently faults will move. But the forces behind the big ones remain complex.
We're still quite a ways from any quantitative forecasting about the when or the details of where.
For a long time, it's been thought that earthquakes occur in cycles. Despite that long-accepted belief, that activity occurs in patterns. The timing of future earthquakes remains mysterious. At the University of Chicago, Dr. Jamie Neely is pioneering ways to forecast earthquakes from a new perspective.
So this is essentially showing all the earthquakes over the last couple of years, and it's showing where they occurred. So the circles here are showing where the earthquakes are occurring, and the size of the circles corresponds to the magnitude of the earthquake.
Jamie investigates how faults behaved during previous quakes using a brand new model.
Traditional models assume that when an earthquake occurs, that all that strain that built up before the earthquake gets released. And so the idea is then that the process starts over again. It sort of renews again. We call it recurrence time between earthquakes. So let's say that on average, an earthquake may occur on a fault every 100 years. But sometimes there's only 50 years between an earthquake. Sometimes there's 150 years. Sometimes there's 300 years between an earthquake there. We know on average how often an earthquake will occur there, but there's a lot of variability in what actually we've observed in the past and likely to observe again in the future.
Forecasting the timing and location of a big one before it happens would be the ultimate way to mitigate loss of life and destruction.
The energy essentially builds up over time. You build up this energy, essentially the strain along the fault, and you can think of it as a sort of an elastic band deforming. And so if you pull on an elastic band, it sort of stretches, and then if you let go, it snaps, and you can think of that as sort of the earthquake happening. If you go a really, really long time between earthquakes, you've built up or accumulated a lot of strain along the fault. When you have an earthquake, you've only released some of that strain. There's what we call residual strain after an earthquake, and that then affects or impacts the timing for the next one. So if you have a lot of residual strain, then the probability of an earthquake occurring sooner is much higher than you would if there was no residual strain. Our new model tries to do a better job of mimicking this process, to have more refined forecasts for the probability of one occurring in the near future.
This new forecasting model is called the long-term fault memory, or LTFM.
So what we have here is our generalized long-term fault memory model. And so what is happening here is that the vertical lines are essentially when an earthquake occurs, and then the dotted lines between that, you can think of it as strain building up between the earthquakes. Or you can think about it as the probability of an earthquake increasing with time.
The LTFM combines the assumed partial strain release from a fault with the specific timing of past earthquakes.
What our model can do is that if you have a very long gap between earthquakes, it can estimate how much residual strain is left over after an earthquake, and then issue an updated forecast for when the next earthquake is going to occur.
This new model can better anticipate large quakes on faults that rupture at irregular intervals.
We are looking specifically right now at the southern San Andreas Fault, but the model could be applied to any fault around the world.
Neely's LTFM factors in the timing and order of previous quakes on the fault and influences whether an earthquake could arrive ahead of schedule. The first test for the LTFM model was applied to the San Andreas Fault because of its history of unexpected earthquakes.
In the continental US, the San Andreas Fault that runs through California has had large earthquakes, in the last 120 years.
Along the Mojave section, traditional models showed that earthquakes seemed to strike approximately every 135 years. But when Neely looked closer, he saw a more erratic schedule. A significant difference between Jamie's new model and former forecasting models is that as more time passes, the likelihood of a large quake continues to increase. The LTFM can estimate the probability of a large earthquake along a given fault over centuries in the future.
We're continuing to work on our long-term fault memory model, and right now we're looking at sort of an individual faults around the world.
One thing that we don't know is if there's a precursor. So is there something that happens before earthquakes occur that we could measure and say, this thing just happened, that means an earthquake is coming? We've looked for them. We did something called the San Andreas Fault Observatory at depth, where we drilled down into the San Andreas Fault, and we didn't find anything. Now, that may be because we didn't know what we were looking for. Maybe because we don't have the sensitivity to measure that.
Big earthquakes leave a monumental path of death and destruction. And in many cases, the quake is only the beginning of the trouble, like with the San Francisco quake in 1906.
The earthquake caused devastation across the city, but the fires that followed were really massive and terribly, terribly destructive. And part of that was because a lot of the piping and the systems had broken during the earthquake, and so they weren't able to fight the fires very effectively.
Some of the world's busiest cities lie on worrisome fault lines, including Mexico City, Tokyo, New York City, Mumbai, Delhi, Shanghai, Kolkata, and Jakarta. And while tsunamis can flood coastal areas, other dangers exist.
Obviously, infrastructure, like the shaking can cause buildings, roads, bridges to collapse. But there's a lot of other hazards associated with it as well. The shaking can cause liquefaction. So that's when you have sort of wet soil. So if you think of sort of landfill in a swampy area, and if there's water in the soil, that shaking essentially causes the soil to lose its strength. So buildings will often like collapse and subside into essentially muck in that case. Landslides are an issue if you live in mountainous areas. Shaking can cause landslides and rock falls in those mountains.
The U.S. has developed early warning systems like USGS Shake Alert, which now operates in California, Oregon, and Washington. This system sends out notifications to residents' mobile devices and to utilities, hospitals, and public transportation.
Shake Alert is an earthquake early warning system. This is not prediction because this comes after an earthquake has already started. The seismometers closest to where that's occurring are going to pick up a certain level of shaking. When they do, they send a notification to a center that assesses that to see if it's going to be a potentially problematic earthquake. If it is, then it sends out an alert to people in the vicinity to say, earthquake shaking is coming. Please prepare for earthquake shaking, and we'll give you a countdown until you feel the shaking in your location.
These mobile alerts don't predict how large the quake will be. They only detect tremors when they begin. But Shake Alert is a huge step in the right direction.
It also has applications for industry and for utilities. So it can slow down trains to prevent derailments. It can open the doors at fire stations to make sure that the doors don't jam shut, trapping the emergency rescue equipment inside. So there's lots of different ways that Shake Alert can make everyone safer.
Still, people who live in earthquake-prone regions need to do what they can to prepare themselves and their families.
Being aware of your surroundings during an earthquake can be really important. If you're inside, generally, and you live in the United States, you want to stay inside. If you're outside, you want to stay outside and move away from all of the things that could potentially fall on you, like wires or tree branches or the outside of buildings.
Scientists already know that it's critical to redouble efforts to construct or retrofit buildings, bridges, and other infrastructures so they're more resilient in the event of large future quakes.
We want to be able to figure out, well, how strong or how stringent should our building codes be? What should we expect in the future? How strong will the shaking be? And how often it occur in the future of a given size?
So the country's engineers
Partly because the building codes.
These precautions will save lives and property. Progress on
Also know, we move forward in time. quake, but it could be 2 days from now, it could be 2 years from now, it could be 100 years from now. Even if we can predict them, we still have to live with them.